Hello, everybody. This is our lab on the Balmer series and the Rydberg constant. In case you guys didn't know who any of us up here are, it's Andrew, Peyton, Allie, and I. And today we will be discussing the, like I said, Balmer series and Rydberg constant. We'll observe the intricate interplay of light rays as they pass through the diffraction grating. A diffraction grating is a precisely manufactured optical surface featuring many closely spaced lines or slits. When light passes through these, it undergoes diffraction, causing the waves to spread out and create an interface pattern. Balmer series pertains to the visible portion of hydrogen's emission spectrum, consisting of several distinct spectral lines that correspond to transitions of electrons between energy levels within the atom. The Rydberg constant within this formula helps predict the energy levels of the electrons in the atoms within a single electron. The Rydberg constant is a cornerstone of atomic physics, and the calculation is 1.09 times 10 to the 7th meters to the negative 1. We'll be able to become more familiar with the use of the hydrogen discharge tube and measuring wavelengths with our diffraction grating.
The purpose of this lab is to verify Balmer's formula. We will do this by using a hydrogen lamp in a dark room that discharges a diffraction grating. We will observe the rays of light and utilize the Rydberg constant by calculating the wavelength. Activity 1. In case you didn't remember what we looked like, this is a picture of Allie, Kobe, Andrew, and myself. For this setup, we used a meter stick that was set on top of a block located 10 centimeters away from the diffraction grating apparatus. We took note of the distance of the two items because that information will be useful later while we perform our calculations. Activity 2. Here, we measured the distance between the left and right emission spectra of hydrogen. We turned off the room lights and looked through the apparatus towards both sides in order to find the distance between the different colors of corresponding light on each side. The visible lights we saw were red, blue, and purple. We used the laser to measure the exact location of the spectrum lines.
All right, our calculations for activity 1, we found the number of lines per unit length of the diffraction grating. So when we used the red laser on the diffraction grating, we found the distances between both of the lines, and then we used those in our calculations, and we ultimately came up with 1,050 lines per millimeter. Okay, for activity 2, we're going to use the Balmer series formula eventually, which is 1 over lambda is equal to r times 1 over 2 squared minus 1 over n squared. And we have our Rydberg constant of 1.097, 10 to the 7 meters to the negative 1. So for finding the opposite side length, we did these calculations of our distances, and we eventually got the opposite side, and then our adjacent side was found from our distance between the diffraction grating and the ruler. So here's our calculations for that, if you guys want to look at that. So now we're going to talk about our blue color wavelength calculation. So over here, these are all our calculations to find this number. So eventually we got the measured value of 443.6 nanometers for our blue wavelength, and compared to our known, which was 435. And our percent error for this was around 1.98%, which was very close to the expected. All right, to find n for the Balmer series, we need to see that hydrogen has quantum numbers. So for the energy shells, we can have like n equals 2, 3, or 4. So over here we have for the color red, it drops from the energy shell 3 to 2, and then that emits a photon, which we see as red. The same thing happens for blue, it goes from 4 to 2, and purple, it goes from 5 to 2. So over here we have an equation where we solve for the n in the Balmer series, and it just verifies that the n for red is 3. So that's what we're going to use for the Rydberg equation. All right, now we're going to find the Rydberg constant, and this is the whole purpose of activity 2. So we have our equation over here, and for the blue wavelength, I've showed you a sample calculation of what we did. We put the wavelength in there, and we have our n is 4 because it jumps from shell 4 to 2, the electron. And our measured value for the Rydberg constant was 1.2039, 10 to the 7 meters to the negative 1. And our expected was the Rydberg constant of 1.097, 10 to the 7 meters to the negative 1. So we had a percent difference in this one of 9.75. We did this for all the colors, and we had an average Rydberg of 1.18, 10 to the 7 meters to the negative 1. And so our overall percent difference was 7.61 for all of our temps. So it was very close, and the results of this lab support that this is the proper equation. It supports what Rydberg found for his constants.
Through this experiment, we were able to show that the Rydberg's constant's known value 1.097 10 to the 7th meters to the negative 1 was very close to our calculated value, and the average of all the colors, which was 1.18 times 10 to the 17th, shown on the spectra, our percent difference was 7.61. And since that value is under 10, it represents that we were precise in our calculations. Above and beyond, back in the 19th century, around 1888, a Swedish physicist named Johannes Rydberg made a groundbreaking discovery that would reshape our understanding of atomic physics. Rydberg's work unfolded with the existing knowledge of spectral lines and atomic structure as he meticulously examined the emission spectrum of hydrogen. What caught his attention was a remarkable mathematical pattern lurking within the wavelengths of spectral lines. This pattern, he realized, could be encapsulated into a concise formula, now famously known as Rydberg's formula. This formula elegantly linked the inversities of spectral line wavelengths to integers representing different energy levels within an atom. In doing so, it laid the very foundation for comprehending the quantized nature of energy levels within an atom. Rydberg's revelation marked a pivotal stride forward in the evolution of quantum mechanics.
So for our apparatus, we have hydrogen discharge tube, diffraction grating, access to a dark room, laser, track to set up apparatus, meter stick, ruler, and finally a laptop. Also, to finish this project, we would just like to thank Colton for all of your help this semester. We couldn't have done it without you.